So welcome to OPTIMA seminar. Today is my pleasure to introduce Dr. Ye Wang, current ARC DECRA Fellow and a lecturer at the School of Mathematics and Statistics at the University of Melbourne. So he got his PhD from Spain, from the university which I find difficult to pronounce, and a UPC, in the area of automatic control, I believe. Yeah. And he got DECRA in 2022. And I think you joined our school like 2 years ago, roughly. Yeah. So his current research interests include model predictive control, optimization learning-based control with application in particular to water energy systems and autonomous systems as well. So today he's gonna talk about his best research.
Yeah, thanks, Rose. Yeah, hello everyone. Yeah. So today I just want to introduce some research result that I've been doing well since my PhD, which maybe roughly more than 10 years ago already. Well, so this is the water system is, I mean, this is kind of like application results. So we want to do some like a control operation for the water distribution systems. But as motivation, well, this research was fully driven by the real world application. This is a system that is I was using while I was in Barcelona doing my PhD. Well, I was in like a control group and working on the control operation to design some like optimization based control for this type of system. And this is the real system, the Barcelona drinking water network in Spain. And also this is just a part of the full network. It's already complicated. So this is quite complex systems. They do have several the water sources. So it's denoted in this like triangle. And the water actually is taken from the water sources, could be multiple sources, and through the pressurized pipes, and then to fulfill some tank in a different location across the city, and through these through the pumps and also valves, and in the end it will satisfy some demands at a different location across the system. So for this type of system, actually, it's quite energy intensive. So which means it consumes a lot of electricity. So that is they have to leave the water from the water sources to different places, perhaps maybe sometime placed in the middle of the hill or mountain, and then fulfill the demand after the tank. So I think a few years ago I was reading some report from like multiple international agency. So in some like urban city, so of course before this AI stuff like booming before, so for the water system in an urban city, maybe it consumes roughly 4%, from 4% to 7% of total electricity consumptions. So which means it consumes a lot of electricity, so mainly for pumping. And after I did my PhD, so I just relocated to Australia, joined the University of Melbourne. So, and also I have a chance to meet some other collaborators in Australia. And one is was a professor now retired from athlete, show me this application, this real system in South Australia. So for this one, so this is the major water transmission pipelines in South Australia. So on the right-hand side, so the water actually taken from this big river. So this river Murray. So actually from New South Wales, between New South Wales and Victoria, and then until so somewhere in the South Australia. So the water was taken also through these several big these pipelines. And then in the middle of this pipeline, they do have these several pump stations and also some storage. And the water is transported from this river to a different region, so near metropolitan area of Adelaide. and then just connect with the distribution network to supply the water to different regions. So so this system also energy intensive. So based on data we can see online. So in 2020, in 2019 to 2020, that year, so the total energy cost is roughly like 86 million Australian dollars. So that's a lot of money. Actually, also, so the system is currently managed by Ice Water, is a single agency of South Australia. So they also invest some money to install some renewable sources like a solar panel just near this big consumption area, for example, near the pump station. So for the system, for this kind of distribution system, I also want to show you the current operation in South Australia. So I think through a visit a few years ago, we have a chance to visit the headquarters of Ice Water. So there's a room called operation room in the headquarters. So there's quite big frames, also a lot of computers. So from that room, actually they can remotely operate all the pump station across the region. And there's several teams actually working in shift, just manually choose operation, just turn on off the pumps remotely. And of course, since they consume a lot of energy, so a lot of electricity, so they can access the national electricity market. So just direct buy the electricity from the market using this spot market price. So they also have some access for this prediction price. So actually, when they choose operation, of course, there's some like a guideline. For example, they want to they have some like a price threshold, so predefined by maybe the other team. Just suggest the operation team that choose the pumping when the price below a certain level. And also, they want to make sure from this room they can operate the pump station and also monitor the water storage, so in some reservoir, in order to meet the water demands. Well, so for us in academic, so in the university, so we also want to do the research. So we want to design the optimization-based control for this type of system. So we need to consider the system, well, it has pressure pipes, pumps, and valves, and most importantly, there's a storage in the system. And by considering these time varying prices and also time varying demands, so if we have some storage, so by intuition we can know that we can shift some like operator from some expensive to some cheap operation. And the goal is that we want to find some kind of real-time automatic control action or operations to minimize the total energy cost. And also at the same time, we need to meet all the water demands. And also when we deploy a control algorithm, so we want to like ensure the system is safe and is reliable, so can be used in long term. So to achieve that, we can basically write like an optimization problem. So and we propose to use like a MPC or economic model predictive control, which is a quite advanced control techniques that can help us to formulate a problem in order to make a good decision. Well, so before I enter the technical details on how to design this economic MPC, I just want, for general audience, I just want to briefly introduce what is MPC. MPC here, well, so in terms of the terminology, so it's called model predictive control. Here, the model actually refers to the system model or system dynamic model. So rather than like pricing optimization, it's like optimization problem is like model. But here, basically, we call model is a dynamic model. So in MPC, we want to use a dynamic model of a system or plant, and then to predict some future evolution of the system in order to choose a good control action or control operation. And basically in MPC, we just want to build like an optimizer or optimization problem. And we'll design some object function and also some constraint. And of course, the model, the system model is included in the constraints. And also sometimes we do have the reference. So that is, we want to drive the system into some given trajectory. It's either a fixed point or time varying references. And also sometimes we, when we compute the object function, we may consider some like information. So since it's along the prediction horizon, so then we need to use some forecast information. So for the MPC, the main task is to formulate an optimization problem. So here's the one. So we have a reference is I just denote by RT. So it could be varying or it could be a constant. And they may have a corresponding reference for the input. So we want to minimize the difference between the system output to the reference point. And we do have a prediction model. So it's a system dynamics model. And X is state, U is the input. And so from the prediction model, we can also output some signal. So it's denoted by Y. And for the system input and system output, sometimes they may have some like a physical constraint or operational constraint to be satisfied. And the last constraint is called state feedback. So that is we at each time step we do take the measurement for the real system and to set as the first predicted state. So in order to initialize this optimization problem. So as shown in this figure there, so the goal is that so for a given reference in that RT, so we want to drive the system output to track this reference RT. And we'll make by solving this optimization problem and also over a horizon. So I just denote by N, so it's an N-step optimization problem. We'll choose the corresponding N control input. So from U0 to UN-1. And as you know here, so by solving this optimization problem, we'll optimize with respect to a sequence of control action. So from U0 to UN-1. And for the MPC, always we just implement the first one. So we consider a receding horizon strategy. So only implement the first one and discard the rest. And we resolve this this problem again over a different time step. So we just solve this optimization problem repeatedly online. So at each time step, and at each time step, we just use the first one. So we will discard the rest. And for the economic model predictive control, so it's a concept come after the MPC appeared. So it's also driven by the application. So economic model predictive control is like a more general form or generalized MPC. So in this case, there's no reference given. So no reference. So instead of minimize a difference between output and the reference, so we want to directly minimize some state cost function. It could be any general function. So here, for example, in the water system, we want to directly minimize the economic cost. And of course, sometimes we have this price signal, and we also need to use a price forecast. So along the horizon. And for the impact of MPC or economic MPC in industry, MPC and economic MPC have been widely used, also widely used in many different applications. So here I just show you some kind of old survey. MP has been used for like a chemical process for processing and automotive industry and so on. So it can be used. It's quite general technique, can be used in different application. And for the impact, so in the control engineering domain, actually MPC perhaps is one of the best control techniques compared to like a traditional like PID control. PID control is quite simple, it's quite easy to implement without solving any optimization problem. But MPC can bring very good performance. So of course by optimality, right? And also compared to the traditional control strategy, MPC can handle the constraints. So especially for that input. So that was a big challenge for using the standard control techniques like PID. PID cannot handle the constraint. So which means when you choose a control signal, it may outside the control input constraints. So we cannot do anything actually for that. And also for the MPC, as many like researcher like invest quite a lot over the past maybe 20 or 30 years, we do have very rigorous theoretical guarantees on the MPC. So it's like a mathematical proofs. So that can be used in practice. Well, so let's move to the technical part. So that's the economic MPC for the water distribution systems. So for the general goal, as we can see before, so for the water system, so we want to minimize pumping engine cost, and we want to meet all the water demands. And also, in order to protect the pumps. So when we choose operation, we also want to find some smooth pump operation in order to, let's say, maximize the life cycle of these physical pumps. And the task for design this economic MPC, so basically, so we first need to find a prediction model for the water system, and also we need to define this cost function and also constraints. So in the end, we'll find this optimizing problem. So here also I want to say that so this is also interdisciplinary problem, because when we build this prediction model, so actually we need the knowledge from this hydraulics. So we need to understand how the system, how this water system behave. So then that is an interdisciplinary problem. So between this control engineering and also civil engineering or water engineering. Well, so for the predictive model, actually we need to model this. So each important elements in the system. So the first one is the tank, is a storage. So for each tank in the system, actually we can apply, let's say, mass balance of volume balance to the tank, and we can find a differential equation. So here is a discrete version of the differential equation. X of I, so is the water depth of the tank I, and so the K is the time. So the water depth of the tank I at the next step is equal to the per time step, and plus the accumulated water to this tank and minus this water to be used later after the tank. So Q in is the inflow to the tank, Q out is outflow from the tank, and then we just use the sampling time and also the area of the tank to transform this water flow to the volume or to the depth. The second element is the pumps. So in a water system, they may have several pump stations, and either set in series or at different branches. And also in each pump station, they may have several pumps, like setting in parallels. So here, we just want to find, let's say, a control-oriented model or simplified model for the control purpose. So here we want to model the outflow from this pump station, and we use an integer variable to denote so how many pumps are turned on. So in this pump station, so it's denoted by this n, and through a function phi. So we want to build this relationship between this integer variable and the outflow through this pump station. And another constraint we need to consider is that it's for the nodes. So there are several junction nodes in the system without the storage capacity. But for this node, we need to make sure the same volume balance or flow by or mass balance should satisfy. So for example, through this node, so they do have like a 2 inflow to this node and also maybe 2 water demand from this node. So the total inflow should be equal to total outflow. And so we can put like a vector function to gather all the nodes to reach this one. So it's a vector function including all the nodes without storage capacity. And the next task is to define the cost function. So from the objective we are considering, the most important one would be the pump energy cost function. So since we choose the decision variable to be that integer variable, so n, so we also want to fit another function to estimate this energy consumption by these n pumps, which are turned on. And also, we know that we could have these time varying electricity prices, and also it's forecasted available along the EMPC horizon. And then if we do the summation over the total pump station, so we have the total pump energy cost. Another part is that we want to, let's say, find the smooth pump operation. So which means we don't want to turn on and turn off the pump too often. So then we can define this smoothness cost function to penalize the change of the input. So here input is those n actually, so those integer variables. And R is just a weighting matrix, so we can tune it. So in order to get this smooth cost function. So in the end, we can build this economic EMPC optimization problem. We want to minimize the total cost over n steps. And this optimization problem is subject to several constraints. The first 2 are from this prediction model. And so for the tank, actually, we know that there's like a physical capacity. So there's an upper bound for this x, for each x. And also, so from the operational point of view, we can also set some minimal like a water depth for each tank to get some lower bound for the x. And for the U, so lower bound is 0. Upper bound, it depends on how many parallel pumps we have in each pump station. And additionally, as highlighted in that red color, so from EMPC, we can also introduce some like a terminal cost and terminal constraint, so which could be very useful when we discuss about derivative guarantees. So I will discuss them later on. And also here, we consider the price forecast and the demand forecast are available along the EMPC prediction horizon. And so at each time t in this time case, so we will solve this optimization problem, and we'll only implement the first one. So we'll discuss the rest, and then in the next time step, we resolve this one, and also with new update of xt. So that is for the new measurement from the system. Well, so in order to, let's say, test this economic EMPC, so we just choose like a open source benchmark. So original one is from UK. It's called Richmond Water Distribution Network. Here also we just tune a little bit. So we just want to start from something simple in order to like verify and get some insight of these new algorithms. So for this one, so we only have one water source from the right-hand side, and there's a tank on the left-hand side is tank A. So and there's one demand after this tank A in this node 10. So in this branch, actually there are 2 pump stations. Pump station 1 has 2 parallel pumps. Pump station 2 has just 1 pump. And using that system dynamic model, so we can build this. We find this single dynamical function for tank A. And for that pumping flow, we need to, because we want to find a model, so with respect to that integer variable. So here we have two integer variables. So N1 is for pump station 1, so it could be like a 0, 1, or 2. So N2 is just 0 or 2, so for pump station 2. So here we just use like a second order polynomial to fit this pumping flow function. And then that will be used in the system dynamics. So in order to update this X. And for the pumping engine cost, we also have this this N1 and N2 integer variable. And so based on the real data, so actually there's a simulator, it's called EPNet. So it's from water engineer or civil engineer. So we can simulate this network through this simulator. And we can get this this flow, this data corresponding to this N1 and N2 values, and also corresponding this the power consumption for these two pump stations. So with those data, actually, we can fit pumping flow relation and also find this this pumping engine cost. So which is another. So here's a linear function. So to this pump engine cost. So in terms of the constraints, so for the tank A, the physical limitation is the maximum height is 3.37. For the lower one, so that's from the guidance from the, let's say, the normal operation for the water system is like we expect to have like a 40% like full storage water stored in this one. So we can set a lower bound, which is 1.4 meter for tank A. And for the pumps, which is the input signal, so the U has two variables, so N1 and N2. So in the pump station 1, we have two pumps. In pump station 2, we just have one pump. So then that's from 0 to 2 or from 0 to 1. And also, when we sample the data from the simulator, we realize so when the first pump station open the full pump, open two pumps, but the second pump station doesn't open any pump. So for that one, actually, we cannot deliver very significant pumping flow, but the energy consumption will be quite high. So we want to like exclude this scenario. So then we just put additional constraint. So N1 has to be greater than N2, N1 minus N2 less than 1. So in order to eliminate this N1 equal to 2 and N2 equal to 0 case. Well, so overall, by considering all these things, and then we can have that optimization problem, EMPC optimization problem. Since we use this second order polynomial, so and also with the integer variable, so in the end, it's a mixed integer QP problem. And of course, we need to use like a numerical optimization algorithm to solve this one. Well, so I think I did the research, I think a few years ago. I think at that time, I was trying to use Groovy to solve this one, but well, due to some reasons or from some testing, Groovy was not able to solve this one. So quite surprisingly. So then we just find some alternative solvers. So I think almost we have to build our own solver in order to solve this mixed integer QP problem. But in the end, we found some like a solver from, I think, from France, so which can solve this one. So now we can get like a numerical results. So here's the results. So we test our EMPC with a simulator. So because that is like an open source benchmark, so we do have that EPNet model in the simulator. So we solved this mixed integer QP problem. So in the computer, and then we pass this optimal contraction to the simulator, and then we'll get back this measurement, which is the water depth in this tank A. And we also do several simulations with different demand profile. So here on the left-hand side, the demand actually, it can be scaled up and down. It's time varying over 1 day, 24 hours. But we can choose what we call base demand is this deep bar. So to scale up and down for this the total demand. And what we want to do is that we want to try with some high demand and low demand to see if the controller, EMPC controller, can find some reasonable or good operations. So with different demand profile, actually we can find on the right hand side. So that is different. Is a tank evolution over, let's say, 4 days simulation. And so something like it starts from the same water depth in the tank, and then varying differently. That's because the demand will be different. So to show you the individual pump operation, so with just one demand or one base demand. So here, one base demand is chosen to be five times that varying demand. So, but in total, it's still like a low demand profile. So here is the pump operation for these 2 pump stations. We also plot that the pattern for that electricity prices. Here we consider also from that benchmark. So they provide this tariff. So very simple one. So it's just 2-period tariff. So there's a high price and low price. So and repeated over the day. And so here with a low demand, we can see that so for the first pump station, so the pump is only operating during the low price period. So that is all peak period. And since demand is low, we just need to like pump a few water in order to satisfy this demand. So we can store the water in the tank and during the peak period, and then later on we can use it when the price is high. And also here in the pump station 2, since there's another like a branch can connect the pipe. So actually we don't have to pump for the pump station 2. So we just need to open one pump in pump station 1, and then the demand can be satisfied. And then the next result is that we just increase the base demand to start this median demand profile. So here, so in the pump station 1, so we still operate with one pump. And so most of pumping actually is across this let's say all peak price period. And so since this demand is increased, so we still need to pump even the price is high. And also we have that smoothness penalty for this pump operation. We don't want to like turn on and turn off pump too often. So here is that we just keep pumping a little bit more. So then even during the high price period, and then turn off. And for the pump station 2, we just operating the pump during the off-peak period. So there's no pumping during the peak period. And we also test with like a high demand profile. So when base demand is increased to 45 liters per second. So here, since the demand is pretty high, so we need the water to satisfy this big demand. So sometimes we need to do a lot of pumping. And for the pump station 1, so it can be seen here as well. During the off-peak period, so we operate 2 pumps. And then during most of like a peak period, so we just turn off one pump, just use one pump. And for the pump station 2, actually we need to pump during most of time because that is so these 2 pump stations are set in series. So if we want to deliver like a larger flow, so we need to like turn on the second pump station. And we also do a comparison in order to, let's say, verify the effectiveness of this EMPC. So we compare with like a simple controller. It's called trigger level controller. So that is based on the amount of water that we store in the tank A, we can turn on turbo pump. Something like if we have a lot of water in the tank A, then we don't have to, we can turn off the pump. If the water level in the tank A is below a certain amount, we can choose either open 1 pump or 2 pumps and also 3 pumps. So we do the comparison across different base demands from 5 until 55, and also for this network, so there's a capacity. So for the demand greater than 55, the base demand greater than 55, it cannot be satisfied. So that is a capacity for the network. So from the comparison here, we just show different cost. Also, we compute the cost per cubic meter pumped through the 2 pump station. And we can see, and also we compute a ratio between these 2 costs per cubic meter. So on the left table, it shows the EMPC result. The right-hand side is the trigger level control results. So we can see that with some low demands, so for example, the base demand is 5, so the cost ratio is higher, like a 2.5 times more expensive for using this trigger level control compared to the EMPC. And when this demand increases, we know that so we have to do the pumping. So no matter how expensive it is, so then the ratio will be close to 1. So that is, there's no difference of these 2 control strategies because we do like a continuous pumping over the whole time. So then cost will be the same. So the next, I just want to give you some brief discussion on this direct guarantee on economic MPC. So the first property the economic MPC can provide us is called recursive feasibility. So with economic MPC, as you can see, that we will solve an optimization problem online. So at each time step. So we need to make sure that at least the problem is feasible. So that is that's what we call the recursive feasibility. So it's something like so from the beginning, if we start a economic MPC controller, want to make sure at any time step in the future, so it will be feasible. And we do have some like a mathematical proof on this one. So for the time being, I wouldn't enter too much detail, but for the brief things, so for that terminal constraint actually plays a big role here. So when we do this mathematical proof for the recursive feasibility. And for that recursive feasibility, we do also have that the robust case. So that is so when the model is not perfect. So here I use W to denote like disturbance or uncertainty to the system. So this uncertainty could affect the system dynamics. So for example, in the water system, the uncertainty could be from the water demand. So we may not have this, let's say, a perfect water demand forecast. And if the demand is not perfect, so then the estimation of these water volumes or water depths in the tank would be not accurate. So here, the uncertainty may be unknown still, but we just one option to consider this, to handle this uncertainty is to consider the uncertainty can be bounded by some known set. So here is big W. And now we can further improve our MPC. So using an approach called constraint tightening approach. So that is, we want to tighten our constraint on the state and on the input a little bit in order to make the controller robust. So with that, we can also have that recursive feasibility guarantee for the robust version of this economic MPC. Another important property, actually in control engineering, we do care a lot for the system stability. So that is, with system dynamics, we are interested in the states of the system can be bounded. And also sometimes it can convert to some equilibrium point. So we call it asymptotic stability. So the technique we are using basically is based on the Lyapunov theory or Lyapunov stability theory. So basically we'll choose a Lyapunov function to prove for a given system dynamics. So the Lyapunov function can satisfy these two conditions. Then the system is stable or convert to some equilibrium points. So for the MPC, so Lyapunov theory has been applied to the standard MPC, and the key task would be how to choose a Lyapunov function for the MPC controller. So with that reference tracking MPC, which is a classical MPC, so the task is quite easy. That is, we just directly use the MPC total cost as a Lyapunov function. Since the cost will decrease over the time because we want to minimize the difference of this error, so the output and the given reference. So the cost converge, and then that is suitable for set as a Lyapunov function. But for the economic MPC, it's not the case because we have those general economic cost function. So which means we cannot use the MPC cost as a Lyapunov function. And so it was a quite challenging problem back to maybe 15 years ago, especially so in academia. So some people from MPC, maybe we still need to learn more from the Lyapunov theory. And there's some people like from like say nonlinear control system with this kind of Lyapunov stability background. So they may not know MPC. So then there's a professor, David Angeli from UK, from Imperial College of London, who's an expert from this nonlinear control background. So knows a lot about the Lyapunov function. And then enter these areas. So he developed actually some theoretical proof on these stability results for economic MPC. So the theory mainly uses based on the dissipativity theory. So it's like a special Lyapunov theory. So the main task is that still how to choose this Lyapunov function. So instead of using MPC cost function, so there's a rotated version of that. And also to guarantee the stability for the economic MPC, surprisingly, so it's quite easy. So that we just impose additional constraint on the terminal cost. So to be equal to a given state. So this state could be the equilibrium point. And then the system after, we still optimize the economic cost, but in the end, at the end of the horizon, we just convert to that point. So then as system runs, so in the end, the system can convert to this excess. Well, so, but come back to the water system. So we want to use the economic MPC. The question is that how to choose these equilibrium points. And also, especially for this water system, so we quickly realize that the economic cost function is a state independent, but Lyapunov function is a state dependent. So basically, it's still really challenging for water system how to choose this Lyapunov function. Well, so okay, so most recently, so with my PhD student Andresa, actually we did some like a theoretical work. So for this water system, it's like motivated by this water system. So we can actually so prove the stability for this economic MPC with state independent cost function. And also from the real system, so we can see that when the demand is periodic and also the price is periodic, we can actually find this like an optimal steady states. So which can be obtained by solving another optimization problem just once. So here, the only difference is that we don't take the measurement to initialize this system. So we just impose like a periodicity constraint. So we want to find a sequence of steady state. So over one period. So this period could be defined by the price or demand or the same. And then by imposing some additional constraint into the MPC, we can really prove and also demonstrate. So we can we have two options. So one option is that we can make sure that the system cost can convert to the optimal one. So that's on the right hand side. Or we can like impose the system still operate economically, but in the end convert to the optimal one. The optimal one is corresponding to the minimum cost in terms of this economic cost. So yeah, I wouldn't explain too much on this paper, but we will also put this paper in archive. Feel free to read it if you are interested. Another key property for the economic MPC is for that the performance in terms of the cost. So here we also have another property showing that the average performance. So that is when we run this MPC in a long time, so the average total cost. So we can prove that it's no worse than the optimal cost we find from this when we find these steady states. So which means we always like operate the economic MPC in a like economic way. But in the end, so just want to quickly summarize the work. So MPC can find some economic MPC can find some good operations and also achieve very good performance for the water system. MPC can have these very strong or very rigorous theoretic guarantees. And those theoretic guarantees actually can provide some guidance when we design the MPC for the practical or real world applications. Some ongoing works. So for that uncertainty, so sometimes maybe it's the stochastic uncertainty and also may not be bounded. So maybe unbounded. So how to address these uncertainties, stochastic uncertainty, is still quite challenging works. Another direction is that nowadays they have a lot of data available from the real world systems. So how to use those data to help us either improve the model of the system or save us some computation, because we still need to solve the optimization problem online. So that will lead to the other research line is called learning-based control or data-driven based control. Yeah, so that will be all my presentation. Yeah, thank you very much.